impossible. It's impossible. In other words, we have the discontinuity in the vertical direction. And the AM composite is actually implying the reinforcement of the particles. So the second half phase within the matrix lies, for example, the glass-filled nylon powders or the paraben sintering, where we have the majority material is metals, for example, and we have the reinforcement of the second half phase in the term of precipitates or in terms of the introduction of the second half phase within the matrix. Yes, and we have the enhancement of the strength based on the Ouro-1 mechanism, which can prevent the movement of dislocation under the presence of the second half phase. So note that the properties of additive manufacturing materials depend on the manufacturers. Among them, those among the most important factors are, for example, processing parameters. Uh, yes, we have more than 180 parameters. So view orientation. Yes, because the properties of the material is anisotropic. Anisotropic. It means that properties in different direction will be different, and the selection of view orientation will strongly influence the properties of materials. So, for example, if you align the part horizontally, yes, the properties will be different if you align it vertically with respect to the building substrate. The geometric design, yes, for sure. So if you would like to use the additive manufacturing to fabricate the very complex structures and very detailed structure with high precision, so you have to think about this because generally speaking, AM cannot be used in order to fabricate the part with high precision because in such a case you have to use post processing in order to fabricate or to post machine the surfaces with higher quality. And please remember that the surface roughness of those parts which are made of additive manufacturing, um, uh, let's say, is larger than 10, even larger than 40 microns. So this cannot be accepted in some cases where the tolerance, where the required tolerance is more than 1 micron. Yeah, so depending on the application that you need to select whether the additive manufacturing process, the hybrid process combining additive manufacturing and traditional subtractive machining, and material feedstock properties. Of course, the properties of input material will have the great influence on the properties of the part after the manufacturing process for sure. The better the input, the better the properties we can obtain after the process of fabrication. But then the challenge is regarding, how can I say, the orientation of the reinforcement, especially for the case of fibers, and because it's impossible to align in a vertical direction like in this in the second figure. Yes, cross plane reinforcement. Yes, and in this slide, on this slide, we see the summary of application for common additive manufacturing methods. And we have a variety of materials for different applications. So, for example, aluminum. Yes, for sure. We were talking about the additive manufacturing materials, not material in general, like in the case of aerospace material. But we have a talk on every Tuesday. We talk in detail about the additive manufacturing methods in the form of either powders or wires. And here, aluminum can be used for fabricating aerospace parts, of course, because it's light. It has, let's say, good strength, good ductilities. Yes, and reasonable fracture toughness. But if the application requires uh, higher strength, and in this case, stainless steel or titanium, for example, are preferable comparing to the case of aluminum, especially if you need to withstand the high temperatures, as I already mentioned to you on Tuesday. So we need the use of nickel-based superalloys for those which need to work at more or less 850 degrees C or around 600 degrees C can be used with part can be used with part those made of titanium or titanium alloys. Let's say alpha plus beta duplex titanium alloys, because please remember that the basket wave structures combined with the equiaxial titanium grains can have a great combination of properties. Yes, where the equiaxial grain can withstand quite good the corrosive environment. So to enhance the corrosion resistance with the alpha phase, and to enhance the strength, we need the presence of the beta phase. And nickel-based alloys, we need the gamma prime. We need the gamma prime, and that's the reason that the nickel content inside the nickel-based superalloy is at least 50%, maybe a little bit smaller than 50, but around 50% at least. Medical, yes, we pay more attention to the stainless steel because, for example, if it's implant in the human body, so it needs to withstand some kind of fluidic, yes, fluid, human fluid. Yeah, I cannot find the words, but generally speaking, is inside body, human body is a corrosive environment. So if you implant with, for example, the skin and with low level of corrosion resistance, and yes, the rust will occur. Rust will occur. Titanium, because it's biocompatible, biocompatible. So it's general speaking, is compatible with the human body. Yeah, and others. Energy, oil, and gas. We use stainless steel to make the pipe, yeah, for transporting the oil, for example, or gas, or to make the vessels for storage purpose. Yes, so I think I can talk a little bit about the automotive applications to the cars. So for the moment, there are many parts which are made of aluminum alloys for sure because it's light. Yes, stainless steel for sure. Titanium, yes. We rarely observe those part equipment in a car which is made of titanium because it's expensive for sure. Yes, so for the others, you can pay more attention to the machinability, wettabilities. Yes, especially in the case of additive manufacturing, we need to pay more also attention to the machinability and wettabilities. The higher ability of wetting, yeah, the easier to be manufactured by the additive manufacturing process. Uh, for example, yeah, under the influence of the heat source like the laser, electron beam, or the plasma. Yeah. High temperature application. This is undoubtedly said that uh, we we pay attention or we use titanium and it can play super alloys. Yeah, for sure. Like in the case of a turbine engine, we used titanium or nickel based super alloy to fabricate the blade of the turbine engine. Mm. And on the right side, you observe the typical materials for particle fusion AM. Yeah, so several common materials are listed here. For example, titanium aluminum 64. Yes, together with some properties like the Young modulus, the ultimate tensile strength, the percentage of elongation, and several AM system that can be used to fabricate these materials. Yes, so it's quite famous to know about the EOS. Yes, I remember that I have I have talked about this slide last week. It's because EOS is a system in which is ooh, uh, this system is fabricated in Munich. In Munich, this is the headquarters of EOS company. And SLM Solution is also a German company located in Lübeck. Yes, right. And the others, yeah, I have heard, but I'm not really familiar with. And the other, for example, 17.4 precipitation hardening stainless steel can also be fabricated by additive manufacturing. Inconel is the nickel-based superalloys, yes. And aluminum silicon tan magnesium is quite famous aluminum alloys that can be fabricated by EOS to obtain, let's say, 100 relative percent density. Yeah. So for the moment, the technology has developed so that for some situations we can obtain, let's say, the material having around 100% relative density, so almost solid. And some may need further treatment, like with hot isostatic pressing, in order to help to improve uh, the relative density or to reduce to the minimum level of porosity. Porosity. Okay. And here there are several materials that can be manufactured by several, let's say, by the butterweb fusion and direct energy depositions. Yeah. So yeah, if you have enough time or you are interested in, just read through it and to get some idea of which material uh, can be easily fabricated by a certain technologies. So for example, aluminum, silicon tan magnesium can be easily fabricated by the laser assisted particle fusion and so on. And it's taken from the progress in material science and published in 2018. So it's not new, not a new paper, but it's relatively new because it's published in 2018, and you may remember that after almost 2 years, so we have the how can I say, the COVID pandemic, and almost everything is suspended. Yeah, so that's the reason that I have mentioned this paper is relatively new, not really new, but solid free form design. Yes, this is one of the advantages of using additive manufacturing, because when you use the free-form design approach, so generally speaking, by using the traditional manufacturing process, not all the cases we can fabricate the part. Yes, if you can see in the case of, let's say, the cuff, uh, which contain the complex porous structures for bond-in growth. We say this is the acetubular cup for the hip implant or the hip joint replacement. Hip joint replacement, and this can be made of either metals, so let's say stainless steel, or uh, polyethylene, maybe. Yes, we can also use polymeric material in order to fabricate the acetubular cup. Yes, for hip joint implant, but I would say that is quite is bio-inspired design for sure, because this rough surface is for bond in growth, so the bond will grow and penetrate to the porosity, and can with the growth of the bond into this porosity, we can fix the position of the cuff on the human body. Yes. And you know, if you use the trace in the manufacturing process, how can you fabricate this rough surface? Yeah, generally speaking, quite difficult, or sometimes almost impossible. However, AM can do that. So we have benefits for filtration or the osteopathic bone growth. Yes, and this is the advantage. One of the advantages of using additive manufacturing. Yes, so we can take the advantage. Um, we can, how can I say, use the approach of solid free from design without thinking of the manufacturing process. Which one can be used to fabricate this design? Yes, because with trace in the manufacturing process, the more complex, the more expensive the parts are. So, and this is not a constraint of additive manufacturing when using additive manufacturing to fabricate the part. So, design structures for providing directional dependent mechanical or thermal properties. So, generally speaking, I would say that this is the disadvantage of using AM because the properties of the material is anisotropic. Yes, but we can consider, because if we can align uh, the direction having good quality to withstand the load, yeah, so this could be okay. It could be okay. So it means that you should design structure in such a way that for certain direction it can withstand in very good manner the external forces or the thermal or to satisfy the requirement of thermal properties. Yeah. And the design might include features for energy absorption, gas fluid flow control, acoustic wave propagation. So, yeah. So because in some cases where you want to implement the internet flow channel, and if it's too complex inside the part, then uh, the traditional drilling process cannot be used to fabricate this type of structures. Casting might be, but not always possible in terms of the quality. In terms of the quality, because casted part has poorer quality than um, those which are made of rotting process, a traditional cutting process, or even additive manufacturing. Design complexity, yes, yes. I would say that there's almost no restriction in terms of the design. So almost all of the design can be fabricated by additive manufacturing. So, but this always has two side effects. Everything has two side effects. Yeah, advantages go together with challenge or difficulties. Yes, uh, but you know that in order to benefit from design complexity when using AI, you need to understand. How can I say, to study more to understand what happened, yeah, beyond the term additive manufacturing and design for additive manufacturing, optimization, yes, and so on. It's not simply the thing that okay, you design, you put it into the mm, uh, you import the design to the additive manufacturing system, uh, you turn on everything and push the button to start. No, it's not simply like this. Yeah. In many cases, we obtain failure after the manufacturing process due to the improper, inappropriate selection of the printing parameters, so, and orientation properly. Design tools, uh, yeah. So we have different design tools. So, for example, fully parametric model-based engineering or CAD. So it means that you have the parameters in order to define the CAD file. But there's always the case that the part is difficult to design by parametric design. So in that case, you use the how can I say? You create the structures with clay, for example, and then you use 3D scanning to scan the part, and you use the software to modify the STL file, yeah, before you set up for printing process. However, the traditional design is based on the parametric model-based engineering. So starting from the sketch, yes, and you create the 3D model and set up the model for printing out the 3D physical object. And even from the CAD files, and even from the conversion process from CAD file to the STL file, the errors can occur. Yes, for example, there's some hole on the surface of the STL file, gap, sharp edges, and the inverse normal vector is being done. So when you convert into the STL file, so the surface model contains a lot of triangular elements, and the normal vector of the triangular elements tend to go outward, defining the external surface of the model. And the inner surface of the elements will restrict the area inside that the laser will scan through. Yeah. And for any reason, the normal vector of an element goes inward. So the software cannot detect which one is the external surface and which one is the internal surface, and the printing process cannot be started, let's say. So you have to fix the issue, the inverse normal vector, before you can print out the model. Non-volumetric geometry and scaling issue. Yeah. And here on the right side, you see another applications, the fuel nozzle. So this already cut, yes, 1/4 of the structures to see the internal features of the fuel nozzle. And you could think of the fact that if we have a rocket or a billet, for example, and with the traditional cutting process, how you can create, yeah, the complex internal features of this fuel nozzle? No, almost impossible. So this can only be done by using additive manufacturing. So this is quite complex, and you can combine multiple components together in order to reduce the number of steps of assembly. Yes, save cost and time for assembly. Yeah. For example, different components of the fuel nozzle structures. And if you need to replace the part and then change the whole parts, so it requires short period of time. And in terms of creating the additive manufacturing design using parametric, so it means that, as I already mentioned, it started from the sketch. So you need to define the dimension based on the variables. You can adjust the model shape by changing the value of variables. So for example, if you define the head or simply the diameter of the internal flow channel is X, and if the diameter is, let's say, 5 millimeters, yes, so the software is create the 5 millimeter diameter for internal flow channel, and because you consider it's a variable, so the values of variable can be changed, and it is 6. Yeah, and the software can modify the design so that this can enlarge the how can I say, the internal flow channels, but to a certain values. Yes. So this is a matter of design of experiment. For example, in the case of ANSYS, you can also design a certain parameters to meet a goal, for example, a goal. Functional features like a shape, reference location, material, yeah, can be also considered when creating the AM design. Yes, because we are talking about the design for additive manufacturing, so we design not only the geometry of the part, I mean the structure of the part, but also design the parameters for the printing process, uh, the parameters for materials. Yes, and these parameters can be a value, a specific value, or can be a variable, which you can provide several inputs for these variable, and we have the modification of the structure accordingly by changing the variables, by changing the values of variable. Let's say x is a variable, and we can assign certain values for x here, like the diameter, x equal to 5 millimeters, and we can change x equal to 6, and so on. Manufacturing features have no functional use, yeah, but aid in manufacturing process. This one you have to pay attention to. In fact, yes. Uh, for the traditional manufacturing process, so if you have at least, if you have one time to see the manufacturing process for the cylinder block of the combustion engine, for example, you will observe there are certain holes, so we call them the technical holes. So this actually uh, not act as a certain function. No, it's only used to assist or to support the manufacturing process only. But practically, for the practical use of combustion engine, we do not use this for any purpose except for assisting the manufacturing process only. So similar to the case of traditional manufacturing process for the combustion engines, as I already mentioned, the cylinder block. Um, in the case of additive manufacturing, yes, for many circumstances, we have to create the manufacturing features, uh, aiding the process of fabrication. But practically, for the operational process, there's no functional use. For example, the powder remover hose for internal AM volumes. So this means that, okay, if you have the closed internal volume, let's say, if you have a closed internal volume, uh, and you use the powder bed fusion technologies in order to print out the part, and after the 3D printing process, the internal is a hole, filled completely with unsintered or unmelted powders. Because you use the powder bed fusion, so the powder will cover layer by layer. Yeah. So if you have the internal volume after the 3D printing process, so the internal volume, like the internal channels or the cavities, will be filled completely with the powders. Because only the regions, for example, the words of the part, will be melted or will be sintered under the influence of the heat source. For the others, the heat source will not irradiate onto. Yes. And if the material is stuck or it entrapped inside the hole, so the overall weight of the part will be enhanced. So we do not obtain the meaning of uh, light part fabrication. And therefore we need to release, to take all of the residual out of the internal volume. This can be done by fabricating the powder remover holes, so that after the additive manufacturing process, the unfabricated powders can be released or can be taken out of the part. Yes. Or in some case, if you want to, let's say, to enhance the qualities of the surface. Yes, because the roughness of the part which are made of additive, which are made by additive manufacturing, is quite poor, just for fun, terrible. And in that case, you need to add uh, additional layers on top of the surface. So we have the residual materials, and once the the additive manufacturing is completed, and then you subject the part to the post machining process, and then you use the traditional milling in order to enhance, to cut the rough surface, and to polish the surface to enhance the qualities of the material, of the surface. Yes. And material define shape features in AM. The minimum one thickness constraint consider material dependent features. Yes, this is one issue. Yes, uh, this is actually the limitation of technologies. And depending on the technologies, for example, powder fusion or direct energy deposition and others, and depend also on the form of the input material, like powder, powder size, powder shape distribution. I'm sorry, powder shape, powder size distribution, and quality of the powder as well. And these parameters will affect the minimum one thickness. Yeah. So for example, you have a thin worm, and if you use the additive manufacturing process, so depending on the input material processing parameters and the minimum values of the worm can be changed. But generally speaking, I would say that is 1 millimeters. And if you tend to fabricate something which is smaller than 1 millimeters, and you, I would say that you have the high probability to have defect. So you have to consider the features based on the uh, technological ability, khả năng công nghệ. Tôi nói kỹ hơn cho các em một chút là về mấy cái feature mà hỗ trợ cho cái vấn đề sản xuất này. Tôi lấy ví dụ là cái block xi lanh ấy, trong cái quá trình mà sản xuất động cơ đốt trong chẳng hạn, thì nó luôn luôn tồn tại những cái lỗ rỗng công nghệ. Những cái lỗ này nó chỉ hỗ trợ cho cái quá trình chế tạo thôi, chỉ trong quá trình chế tạo nó hỗ trợ cái quá trình đó, còn khi mà đưa vào sử dụng thì cái lỗ này người ta bịt lại, nó chả nhằm mục đích gì cả trong quá trình sử dụng. Đối với quá trình additive manufacturing thì cũng có những cái feature, những cái đặc điểm về mặt hình học, cũng chỉ nhằm để hỗ trợ cho cái quá trình chế tạo bằng cái phương pháp additive manufacturing, còn về thực tế thì nó không đóng một cái vai trò gì cả. Tôi lấy ví dụ như là powder remover holes, đấy là những cái lỗ dùng để thoát cái lượng powder dư, những cái lượng bột dư sau quá trình chế tạo, đặc biệt là đối với những chi tiết mà có cái không gian ở bên trong, và không gian này thì lại đóng kín, hoặc có những cái lỗ nó nhỏ quá và cái lượng powder bên trong thì không thoát ra ngoài được. Đây chúng ta biết là trên một cái cross section thì là cái tia laser hoặc là cái tia electron beam nó chỉ quét qua những cái vùng vật liệu, đúng không ạ, mà nó cần quét qua. Có nghĩa là cross section nó đã định nghĩa bởi quá trình slicing process rồi. Thế còn những cái vùng mà vốn dĩ nó là cavity ấy, cái lỗ hoặc là cái hang động, và thì sao ạ? Thì tia laser nó không quét qua phần đó, cho nên là nếu mà dùng cái powder bed fusion technologies thì powder nó vẫn cover, vẫn cốt vào ở những cái vùng đó, vẫn ở trong những cái vùng đó. Tia laser nó không sinter hoặc là không melt những cái vùng như vậy, thì những cái powder ở những cái trong cái cavity nó vẫn tồn tại, và nó vẫn là những cái bột tách biệt nhau, và sau cái quá trình sintering process hay là quá trình melting process thì sao ạ? Cái vật của chúng ta hoàn thành, nhưng mà powder nó vẫn bị giữ ở bên trong, nó làm tăng cái khối lượng của cả cái chi tiết lên, đúng không ạ? Và đương nhiên là chúng ta phải làm sao thoát, lấy ra những cái powder ở tận sâu bên trong đó. Lấy bằng cách nào? Người ta chế tạo ra những cái lỗ rỗng công nghệ, hoặc những cái đường dẫn để dẫn cái lượng powder dư đấy ra bên ngoài sau quá trình additive manufacturing. Thì thực ra là nó chỉ hỗ trợ, có mỗi cái vấn đề là gì, lấy cái powder sau cái quá trình chúng ta sản xuất. Còn lại trên thực tế khi mà đưa vào sử dụng thì cái lỗ đấy nó không đóng một cái vai trò gì cả. Other features like inspection features, cleaning, powder remover, or post-processing finishing features may also be considered. Yes, and on the right side you can see that you can how can I say, combining the traditional design and design for additive manufacturing to design the part for this process. So for example, here, if you could see my the point, the arrow of my mouse, yeah, is moving around the part, the design, and on the left side of the diagram, let's say, we have the constraint or the preserve features. Yes, and if you want to join different channels together, and you just define the way of the joining tools, and then you use the sweep features in CAD, yes, in order to join these parts together, and then you have the model that can be fabricated by additive manufacturing. But I would say that generally speaking, for traditional manufacturing process, it's hard to do. Casting may be possible, but not for the others. Like for example, you have a billet and you drilling process in order to drill the holes. So no, it's impossible to create the curve, the holes having the curves like this. Now the straight holes is okay, but the hole with changing direction like this, so it's impossible to be created. Traditional manufacturing process like foundry, casting, yes, this is the design freedom offered by the AM. Yeah. So for the foundry or casting process, you need the melt furnace, you need the mold preparation. In the case of machine shop, like the shop, which can use the cutting processes in order to fabricate the part, you need multiple equipments. You need the multiple equipment in order to, how can I say, machine these parts, like milling machines for polishing, lead cutting machines, surface grinder, drilling press, drilling one, sorry, electrode-extract machining, yeah, and boring machines. So it's like something like drilling. Whereas in the case of AM, you have the you may need the furnace in order to use heat treatment to modify the properties of the materials. So you have something in mind about the heat treatment process to modify properties of the materials, and it can also be applied for modifying properties of the additive manufactured materials. Cutting equipment, polishing, yes, for post machining as well, and printer. So you need a certain combined use of equipment in order to fabricate the part. And in view of these, let's say, comparison, yeah, not really comparison, but just listing several equipment go together with a certain fabricating technologies. So we can see, or you can point out some of the AM design freedom. First of all, is free from the commercial chef. Because generally speaking, these input material are available. Yes, So for example, when you have bought steam on the market, so the steam are available in form of the sheet, of the pies, of the angles, or the rods. So you tend to buy in powders. So it's expensive because the commercial chef, the commercial products are available. And if you ask for something uh, which is not yet commercialized, so it's expensive for sure. But you can free from the commercial chef. So let's say, for example, if you create the workshop by steel structure, so you use the anchor steel, rod, and sheet, wet them together based on a certain design, and you have the shop. Okay. But with AM, yeah, you are free from the commercial chef. So there is no restriction in terms of the chef. Let's say freedom from process shape constraint. Yes. For example, if you the drilling process in order to create a hole, so okay, you have the straight hole like this, you have the straight hole like this. But if you want to create the curve, yes, or or the complex internal flow channel inside a van, for example. So with the traditional manufacturing process, you have a big constraint of the process shape. Do you understand the point? For example, nếu như các bạn dùng các cái phương pháp gia công truyền thống á, thì nó phụ thuộc rất là nhiều bởi cái quá trình gia công. Cái quá trình gia công ấy chỉ cho phép ví dụ gia công các cái lỗ thẳng, cuối cùng các bạn chỉ được lỗ thẳng. Nếu mà muốn các lỗ cắt nhau thì phải cho nó cắt từ hai hướng vào, đúng không ạ? Còn nếu như các bạn muốn chế tạo ra những cái chi tiết mà có dạng đường cong phức tạp mà nó lại tồn tại ở bên trong chi tiết, thì rõ ràng các phương pháp gia công truyền thống, ví dụ như quá trình khoan chẳng hạn, hoàn toàn không khả thi, không thể làm được để tạo ra những cái kết cấu có hình dạng như vậy. Và AM thì làm được, cho nên nó freedom from process shape constraint. Freedom from post machining constraint like tool reach access. Yeah, it depends on the case. Can contribute one part, can combine, sorry, one part to complex part. So on the right side, you see the first part contains 8 components, and by designing for additive manufacturing, you can combine 8 parts into one part. And yes, you can somehow reduce the weight of the whole part, 40% lighter, 20% stronger, and you also reduce the time for assembling. Yeah. And can reduce the waste materials by machining. Yeah, for sure, because we consider the near-net shape design. So after the fabrication, if necessary, we just need to eliminate a small amount of materials for finishing, and that's all. So we can save a lot of materials during the manufacturing process. Can design complex internal passageway. 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 Yes, for sure. Can create the rigid and lightweight pass. Yeah, just some information for you, because this may be clearer if I find for you several examples here, in addition to the one already on this slide. But and yeah, it's not always easy to find from the published papers. Can design to optimize our aerodynamic flow. Yes, you can add features. There's no problem because you work with the how can I say, computer aided design software. You can modify whatever you want, optimize the design, yes, set up again, and run the AM machines, and that's all. So the optimization process can go through several iteration. So, yeah, freeform to integrate complex rotational feature. Freeform to integrate damping and isolation features for controlling acoustic and vibration. Just some information for you. So yes, because even the writers who have written the textbook. Yes, they have summarized some information from journal papers. So it's quite just, let's say it's a basic, yeah, things. Just list some AM design freedoms. Yes. So there's no problem. There's not actually an issue if you want to integrate the complex rotational features, yes, to your design, because you are free from modifying the design by using, for example, Inventor or SolidWorks. Yeah. Can design custom shape reservoir for pressure control. Can add lightweight support for and stiffen it. Yeah, yeah. The lightweight support can be generated during the design process with the computer-aided design software, or even by uh, the software can, those can be used to set up the 3D printing process. Yeah, you can also add these features uh, during the setup. May change material during the AM process. Yeah, I'm not sure about this because this is preferable to use one type of materials. The presence of the second material during the process of fabrication can be considered as the impurities or contamination. So I'm not sure regarding the AM process uh, for printing out metallic parts. Can create porous structures. Yeah, this actually depends on the ability of the software. Yeah, to just define the reasons and implement these features to to your design. The ability to fabricate parts from the tungsten or superalloy, yeah, those are very difficult for fabrication by creation and manufacturing process. Yeah. These very high melting temperatures materials. So they use additive manufacturing, but not the polymer fusion. They use the other technologies to combine the material together. Design build pass on demand in remote locations. So, yes, this is somehow freedom. Yeah, freedom. This means that okay, this is necessary to fabricate parts in a remote region, in a dangerous region, for example. You transport the machine there together with the feedstock area set up with the robot and so on. And you can design and build part on demand and on site. Yes, I think that we should stop for 10 minutes and we can resume the class after, so let's say at 1 p.m.